All right, so begin with recitation 7. And let's start with the very first problem. This is probably better. Delete it manually. So the first problem, block of mass M is placed on a wedge inclined at angle theta. So as you can see, we continue applying the Newton's laws to different situations and different problems. So this is the situation we have. So we have a wedge and then a block sitting on it. Right? And the condition is that can you hear me fine?
Yes, sir.
Okay, thank you. All right, so it's the block is, the wedge is resting on a horizontal surface, and it's fixed, so it cannot move. The wedge is fixed. Okay. Let's say there are anchors or nails that are stopping it from moving, and the mass of this block is M. Now it's a trivial problem, so the first part sounds trivial, and it is the A part asks to just find the acceleration of the block. Okay, and most of you probably remember the answer without even solving it. If this angle is theta, then A is simply, the acceleration is simply g sine theta in this direction. Okay, but I want to develop some, because to answer the second part of the question better, and also to show that if you choose a different frame of reference, so this answer is very straightforward. If you choose the axis in such a way that this is Ex and this is Ey. All right, but let's not tilt the axis and try to solve this problem in our more conventional set choice of the coordinate system. Okay, so if we choose the coordinate system to be like this, we have x in this direction and y in this direction. Ex and Ey, right? So, and then do a free body diagram. So initially we are interested in the acceleration of the block body. Okay, so make a free body diagram and all the forces that are acting on the block. Most obvious one, the weight downwards, and the normal force, and we are ignoring friction here, and the normal force here, right? And now, how do we solve this problem? So this time we do not have the coordinate system in this direction. It's not very difficult to solve it with this choice of the coordinate system. in this case, you have weight coming down here, while your coordinate system is like this. So we resolve the weight into its components. Okay. Then the expression for the acceleration is simple, because the acceleration in the orthogonal direction, in this direction, we can just take it 0, and in this direction, we just take the acceleration equal to the force, the weight component of the block in this direction. It's very simple. It's also not that difficult here as well. So what you have is weight is in the negative direction. So, and you can resolve the normal force. And I think the only care that you have to give is that it makes an angle theta with the vertical like this, and then you can resolve the normal force. Okay? And this would be n cosine theta, and this would be n sine theta, where this is n, okay, the normal force. And then we get, like we always do, the two equations. Sum of all forces is equal to mass times acceleration. We just write the equations in components. So first we write for the x component and what forces are acting in the x component along the x-axis, what forces are acting along the x-axis. Just the normal force, right? And sine acting along the x-axis. There is no other force in the x direction, negative or positive. So this would be n sine theta, and this would be now m mass times the acceleration in the x direction. Remember, we're dealing with the x component. Okay? So there would be acceleration in this direction. The x component of the acceleration. Of course, the total acceleration would be still in this direction, but now it will have two components, the x component and a y component. Okay, so this is the equation for the x component, and then we write the equation for y component. So in y direction, we have the weight in our coordinate system. This is the negative force acting downwards, so the y is pointing upwards, plus n cosine theta, the normal force acting along y-axis, parallel to the y-axis, is equal to MAY. Right? So we get two equations and three unknowns. If we have the AY, which we don't know. We have AX and AY, which we don't know, but we also don't know what the normal force is. In this case, it's relatively simpler because we get a very simple constraint equation and we assume that there is no acceleration in the direction of the normal force. So that just simply gives us the normal force, and the normal force is not resolved. So the normal force equal to weight. The normal force equal to this component of the weight. But we cannot impose that condition in here. We cannot set any of these components to 0 because these total acceleration in this new frame of reference or this new coordinate system that we have used, both AX and AY are non-zero. Okay. We still have to find a way to solve this equation. Well, what we can do is, you see, if the acceleration is in this direction, okay, then you can write the components of acceleration. So let's say this is total acceleration, this is AX, and this is AY. we see or if you like, you can just be consistent. So you have the y component here and x component here. Okay. And then this is angle theta. So this would be the x component of the acceleration would be ax e cosine theta, and you see the acceleration is in the positive x-axis, along the positive x-axis, and ay the negative a sine theta. And negative because the y component of the acceleration is downwards, so the y-axis points upwards. So now here, if you substitute these two values in here, you have actually gone from two unknowns ax and ay to just one unknown with about the acceleration, and the one unknown is the normal force. Now with two equations and two unknowns, you can solve this system. Okay, let me just erase ax here and substitute the value of ax here. A cosine theta, and value of ay would be minus a sine theta, right? Now from here, it's very simple to just simultaneously solve these two equations and find the acceleration. Can you do that? For example, from this equation, the first one, you can find the normal. The normal force turns out to be ma cosine theta over sine theta, and then substitute this in here. Okay, and then simplify. And the answer that you would get would be the same as before. A b sine theta. Okay, so the acceleration along the face of the wedge would be still a is equal to d sine theta. So the one point that we learned from here is the choice of coordinate system does not matter, and the second point is that we would see in a moment. Okay, so why we needed to use this coordinate system instead of the tilted one. Okay, it made a little bit these equations a little bit more involved, but it would make the second part much simpler. This choice of coordinate system. Any questions so far? The second part of this problem is second part of the problem is that this wedge is now allowed to move. It is no more fixed with the ground. And the equation of motion, so now we have to write the equation of motion or this the force acceleration equation or the forces and free body diagram for the wedge as well. All right. So for the block, the free body diagram remains unchanged and the forces remain unchanged in the coordinate system that we just worked out. X. Right. And they, so when I can write the equations like this. It's exactly what we worked out in the part B. MAY and sine theta MX. All right. And now we look at the wedge. So can you help me identify the forces?
Yes, sir.
One of them is going to be, let's say that the mass of the wedge is capital M and the block is lowercase m. Okay. So this is the force that is weight of the wedge. Then there is going to be a normal force. And to distinguish it from the normal force that we are dealing with here, let's call this normal force on the wedge by the ground. Okay. WG. But other force is acting on the wedge. Now I really want you to answer this.
सर एक वो बेसिकली वो एक्सेलरेशन के साथ आगे मूव कर रहा है तो वो MAX भी तो उसके ऊपर एक फोर्स होगी ना MA जो कैपिटल A है
Can you hear me?
यस सर
जी दोबारा बताएं क्या आपने बताया सॉरी
सर मैं कह रही हूँ जो वेज है इट्स मूविंग एट अ एक्सेलरेशन ऑफ कैपिटल A तो उसके ऊपर एक फोर्स MA भी तो होगी ना M कैपिटल A टुवर्ड्स द राइट टुवर्ड्स द वेज और वेज की मैं बात कर रही हूँ
नहीं लेकिन अभी हमने ये नहीं पता कि हमें ये वेज किस तरफ मूव कर रहा है दैट्स द क्वेश्चन वी नीड टू फाइंड आउट सो दैट्स द क्वेश्चन वी नीड टू फाइंड आउट एंड दैट्स ऑल
एक्सेलरेशन की डायरेक्शन दी हुई है टुवर्ड्स द राइट तो आई अज्यूम कि इट वुड आल्सो मूव टुवर्ड द राइट
नहीं वो दैट शुड नॉट बी देयर सो okay so we don't know what direction the acceleration is going to be before finding it out we can't tell the direction of a vector
सही
all right so but so this is very important that we get this and we get this right yes and somebody has answered it as well that you have to when you look at so this is the wedge and you have already been told that there is only one action at a distance force that we would be considering okay non-contact force and that I've already written here the weight of the wedge okay any other force that acts on this wedge has to be a contact force they are very easy to identify because you just look around the object and see how many which other objects it is touching interacting or tied to or somehow connected to physically how many objects this object is touching two which ones
the ground and the block
the ground and the block the second force definitely is by the block on the wedge okay and to make sense of it so if you look at the normal force okay there is a component of the normal force we did in the previous part okay sorry it should be on the other side because otherwise so this is theta and this is n cosine theta, okay, and the y component, sorry, this x component would be, if I could just write it here, is n sine theta. Okay. Now, the block exerts a force on this object, and that is equal to this normal force here. This is an action reaction pair. The normal force is being exerted by the wedge on the block, and there is a reaction equal in magnitude, opposite in direction by the block on the wedge. Okay, so its components would be just the same, n cosine theta and n sine theta, but in the opposite direction with negative sign, okay, in our coordinate system. So there would be a force like this. Okay, so now if I want to write the first the equation in x-axis for the wedge, again the sum of all forces ma ln, let's assume a is the acceleration along the x component of the acceleration. Okay, so, or let's keep it general for now. And then write the x component, sorry. Okay, so how many forces now? So in the free body diagram now, you have a downwards force, which is minus, or just n cosine theta. We would add minus in the equation. It's clear by the arrow. And then there is a force in this direction, which is n sine theta. Okay, the total 4 forces acting on this. Is this clear now? Or if there is any confusion, you can ask now. All right. So first write the x component. So in the x-axis, I have minus n sine theta equals ma. I'm assuming that a is the x component of the acceleration of the wedge. Okay. So the second equation that we would get in the other coordinate direction would be the normal force by the ground on the wedge upwards in the positive direction minus n cosine theta by the block downwards and minus the weight of the wedge and equals to acceleration in the y direction. And it is given that this block is not neither penetrating into the earth or is not, nor is it jumping off the earth. So it moves along the horizontal surface. So we can just set this to 0. Okay. So this equation is not very interesting because it does not involve the quantity that we are looking for. We are looking for acceleration A. We need to find out acceleration A. It doesn't involve here. But these three equations are interesting. The first one, this, second, this, and third, this. Okay. And in this case, now we have 4 unknowns and 3 equations. The 4 unknowns are the normal force, the x component of the acceleration, the y component of the acceleration, and the acceleration of the wedge. So the small a denote the acceleration of the block, and the capital A denotes the acceleration in the horizontal direction of the wedge, which we have to find out. So how do we do that? So we do the same trick again. Okay. So here substitute ax and ay with their components, and ay is minus a sine theta, and this is a cosine theta, right? Okay, and once you do that, you can solve these equations for n and the acceleration. Now you have just in these two equations, you just have the two unknowns and the two equations. So solve the first two equations to get the normal force n and the acceleration. So we know the acceleration turns out to be g sine theta. And what would be the normal force? And can you figure out n from here?
इसके हिसाब से n हमारे पास आ जाएगी mg cos theta.
mg cos theta or ma cosine theta?
a की वैल्यू g sin theta से सब्स्टिट्यूट नहीं करनी.
Uh, just a minute. Yes, so so you have a g sine theta, and what is the normal force then?
mg cos theta.
Mg cosine theta. Okay, so then you substitute the mg cosine theta here in this equation, the value of n, and this would then give you acceleration a equals m over m minus m over m g sine theta cosine theta. Is this correct then? Okay, substituting, so you get a and n from these two equations. Okay, and then you substitute both a and n in here. Okay, sorry, just the n, so not a n, just the n here, and then you rearrange the terms and you get the acceleration of the wedge. Okay, and this negative sign indicates that wedge would be actually accelerating in this direction. It also makes sense if you look at the forces, all other forces, the vertical forces are canceling each other. There is no acceleration. The net force is leftwards. Okay. As this block slides down, the wedge slides leftwards. Okay. And this would be its acceleration. And as you see, that the ratio of the two masses appear in the expression. So if the wedge was very, very heavy, then it most likely won't slide. Is this clear?
तो सर इसमें बेसिकली हम ये कहेंगे कि अगर ब्लॉक और जो वेज है उसके मास के रेशियोज में बहुत ज्यादा फर्क हुआ तो फिर इट वोंट स्लाइड, या बहुत एक स्मॉल अमाउंट होगी, राइट?
हाँ, बिल्कुल बिल्कुल.
सर
If m is very large and this is very small, then this acceleration would be very small. Okay. But you see that the wedge is not, there is no external force. Okay, it's just the push of the block that is making the wedge move leftwards. This is probably related to why things slip under the weight of our feet. When you push something uneven with your feet, it just slips away. Okay, so what is the next problem that we have? I think the second one you have in your notes, so I'll just go to third one. I think you have this in your notes as well, but let's try to do it quickly. So we have a rod, that vertical rod that is rotating, and then a ball of certain mass attached to it through two strings or two ropes, if you like. Okay. Each rope is of length L, and this is D. Okay. And the rope makes, each rope makes an angle theta with the horizontal. And the question is, what is the question? Yes, the strings are attached to a rotating rod. How fast should the rod rotate that the ball does not fall down? Or in other words, both strings remain stretched. Find the tension in each string. So the question is that, for example, if this ball is attached through two strings and you know that strings are not rigid sport, there is no reason for this ball to be here if you're not rotating. It would just fall down, okay? It would just fall down. And for this ball to keep stretched there, the only way is if you keep moving or keep rotating this rod. And again, if you rotate very slowly, then there may not be enough tension in the strings to keep it there, and it may still fall down. So that is what we need to find out, the minimum rotation speed that would keep this ball stretched there at this position. Okay. And the other question is we need to find out the tension. So again, we start with the free body diagram of this object. Now there would be tension T1 in this string. Okay. And there would be tension T2 in this string. So this would be acting this direction, and T1 would be acting in this direction. And then of course there is the weight. So let's try to write all the forces. Okay. Can you already just count the number of forces acting on this mass quickly and get a number? How many forces are acting on this?
सर एक तो इसका वेट हो जाएगा, उसके बाद आपके पास x component of the tensions हो जाएगा.
Well, let's not talk about components just. Okay. In general, give me number of forces without components.
सिर्फ वेट होगा फिर तो.
Weight and no other force?
नॉर्मल फोर्स, लेकिन ये I don't think ये किसी surface से touch नहीं हो रहा.
Yes, but it's connected, is connected through ropes, by ropes to this. So there are two connections, two physical objects touching this up, two more forces at least, the T1 and T2. T1 and T2. So three forces in total. Okay. So this is a quick way of look at the object and look at, so the one non-contact force doesn't matter. So whether it is touching anything or not, the mass or the weight, and two other contacts. So two more forces, T1, T2, and its weight, three forces in total. Now we resolve them in components to deal with them. Okay. So tension T1, tension T2, and the weight mg, and you can just write the components. So angle theta and okay, so this would be T1 sine theta upwards, and this would be minus, or if I don't write the minus yet before the equation, this would be T sine theta downwards. And then in this direction, I have two components of tension, T1 cosine theta and T2 cosine theta. Okay, all the components. So now we write the equation for the x component first, for example. So what would be that? Let's first write for the y component because it's simpler. T1 sine theta upwards, this minus T2 sine theta downwards, and the weight mg, and we are assuming that this object stays there, okay, does not fall down, so the acceleration is 0 in the y direction. So this would be one equation. Okay. Okay. Now the second equation, T1 cosine theta plus T2 cosine theta, the tension. And is there any other force in the x direction? No other force. How about the acceleration? What about the acceleration?
सर T1 cos theta plus T2 cos theta नेगेटिव नहीं होंगे क्योंकि वो लेफ्ट साइड पे जा रहे हैं.
Yes, I have just tried to trick you, but you are not buying it, right? So both of them are minus, okay? And so, okay, fine, that's fine. Let's keep them minus. But what about the acceleration here? Is it 0?
सर उसकी एक्सेलरेशन 0 नहीं होगी. आई थिंक उसकी एक्सेलरेशन कांस्टेंट होगी probably.
But what would be the acceleration? Because this object is rotating in a circle, okay? This makes a circle, no? Doesn't it make a circle in the along the x plane, in the x plane? No?
बिल्कुल.
So if it does that, then the acceleration would be what?
Omega square r.
Omega square r. Good. Is it r square omega or omega square r? Omega square r, I think. Okay. Okay.
Yes.
Now, depending on whether it is rotating this way, clockwise or anti-clockwise, the acceleration can be negative or positive, right? So That's an arbitrary choice, is not specified, and it doesn't really matter for to answer our question which way. So I take the acceleration negative. Okay. So I say let's it's rotating this way in this direction. So I take the acceleration negative and cancel all the minuses, make them all positive. Okay. So just keep the equation simple. Okay. So we got two equations now, and we can solve these two equations for T1 and T2. Okay. So first you can do is you can just add these two equations. Okay. Take the sign outside and divide it on the other side and then add these equations. So what I'm saying is write this equation like this. The first one, T1 plus T1 minus T2 is equal to mg over sine theta. First equation like this. And the second equation you can write T1 plus T2 equals m omega square r over cosine theta. All right. So if you add the T2, if you add these two equations, this would cancel. You'll get 2T1 times sum of these two terms. Okay. And then if you subtract this equation or this equation from the other, you would get T2. So I'll just move on to the next board. And write directly the expression. So you'll get T1 equals half mg over sine theta plus mr omega squared over cosine theta, right? And T2 turns out to be half minus mg over sine theta plus mr omega squared over cosine theta. Right? So now we need to analyze this in a limit. So let's say that you stop rotating. Okay? What happens to T1?
Sir, अगर हम it would become O equals to mg sine theta, I think.
Yes, so this term goes to 0. Stop rotating means omega 0. So this term goes to 0. And the T1, the tension in the upper string would be proportional to the weight because it still has to weight. Okay, it has the weight to hold. But what happens to T2 if you stop rotating? Yeah. Imagine these are just magnitudes, the mass, the acceleration, and sine theta in the limit 0 to 90 is positive. So what happens is if you stop rotating, the tension in the second string becomes negative. Okay, is no more stretched. So the lower string, if you are not rotating, and it also makes sense because the object would be falling, is no more stretching, is no more pulling on this string. Okay. The rod is no more pulling on the object, and the object is no more pulling on the rope. Okay, so the tension would become negative. That would mean that this rope would start buckling, if you like. Okay, and that is kind of gives us the condition for what should be the minimum rotation frequency. That would, so we need at least as much rotation so that this term remains bigger than this term and we get a positive tension. So the object stays there stretched with the lower string stretched. So this gives you the condition that mr omega square over cosine theta remains greater than mg over sine theta. You can now you can solve it for omega yourself, right? Any question about this? So do we have seven? We have 7 minutes. So let's quickly solve the fourth problem as well. Okay. The fourth problem is that you have an amusement rotor. So an amusement rotor is a big cylinder, and people just walk in and stand against the wall. Okay. Then once the people are positioned inside the rotor, it starts rotating at a certain frequency omega. So as you can imagine, as they are rotating, the people if you're standing in the cylinder and then it's rotating, so you start pushing against the wall, and at some point, once it has achieved a sufficient rotation velocity, the base of the rotor is dropped, but nobody falls down. Okay, that is the trick. And the question is, what is the maximum? Let me just read the question quickly. Find the minimum spin speed for which you would not fall down. Assume static friction to be mu s. So here we have to invoke the force of friction. So let me just quickly introduce, because we haven't formally introduced the force of friction in this course. So if you have two surfaces touching each other, okay, so there is definitely force of friction between them. There's some features of the force of friction. One of the force of the friction feature is that it always resists motion. Okay, so that means if you're not moving, then there is really no force acting on, no force of friction is acting on this object. So the force of friction starts acting on the object when you're moving with a particular force. Okay, let's say you're acting on this with a force F. A force of friction would start acting on this object. It's always in the opposite direction of motion. Force of friction is always in the opposite direction of the motion because it has to resist. Its value can be small, and it maxes out to, it always becomes equal to the force but not greater than the force. Okay, because it's a reaction force, is a resistance force, dissipation force. It cannot be greater than the force because friction cannot move. There is no acceleration associated with the friction as itself. And quantitatively, if the normal force acting on this object by the other surface, this lower surface, is N. If this is the force acting on this block, this object, by the other surface involved in the friction, remember, is always between two surfaces and is a type of contact force. And there is an empirically obtained proportionality constant that relates the normal force and the force of friction. It is the coefficient of friction, is dimensionless. So mu s, I would introduce force of friction hopefully in more detail in one of the lessons. Okay, this gives you the force of static friction. There is a force of dynamic friction. We would talk about kinetic friction. We'll talk about that as well. But that's enough. So two surfaces touching, pushing each other. And then if you try to move my hand, for example, up and down, and let's say that I try to move my hand up and down without really sliding. Okay, so the force that is stopping my hand from sliding on this board is this force. Okay, it never is greater than the actual force that is causing the motion. Okay. So what stops people? So let's try to make a free body diagram of a person inside the rotor. Okay. So this is the wall, and this is the person, and the wall is going in a circle. It's moving in a circle, and then so it's the weight of the person that is acting downwards, and in the opposite direction you would have Fs. Okay. But where is the normal force then? Where is the normal force coming from? This is the person, and this is the surface here. Okay. The surface exerts a normal force on this person. So the forces in the y direction are simply Fs upwards minus the weight. Okay. And they have to be 0, because if you accelerate in the y direction, that means you're falling down. Okay. So the force of friction has to be equal to the weight of the person, and force of friction we just said that is equal to mu s n minus mg equals to 0. So what is the normal force then? Anyone?
सर अगर
आपकी आवाज कट गई है रिको।
सर मैं कह रही थी कि हमारे पास अगर इसकी रोटेशन की एक्सेलरेशन ओमेगा है तो आई थिंक नॉर्मल फोर्स वुड बी इक्वल्स टू m ओमेगा स्क्वायर r आई थिंक क्योंकि
Yes, exactly, yes. So this is exerting the normal force, and it is causing an acceleration in this direction. That is the centripetal acceleration. So n is m omega square r minus mg equals to 0. And then you can solve this equation for omega, and I think it turns out to be g over mu s r. Okay, so this would be the minimum rotation frequency that you need the rotor to rotate for the people to not fall. Okay, and interestingly, look here, that this is the condition does not depend on the weight of the mass of the person. So it doesn't really matter how heavy a person is, okay, what weight a particular person has. It only depends on the radius of the rotor. Okay, if you have a bigger rotor, you can rotate slowly, but if you have a relatively shorter rotor, then you will have to rotate very fast. Okay, to keep this to maintain this value, and it's g is just a constant for the ground purposes. The mu s is the coefficient of static friction. Okay, now mu s can also depend on what you're wearing, because it's really the friction between your back and of course if you're wearing different clothes, then and let's say that the surface of rotor, okay, the surface of rotor is usually fixed, so people are wearing different clothes. So so to be safe, what the people in the amusement park usually is that whatever number they get for this omega, they usually rotate at a much larger frequency than what they get, the minimum frequency that they need to hold people with the wall. Okay, and that's it. Thank you very much. And if you have any questions, I'll be happy to answer.